Okay guys, so now we're actually going to do a problem. So this is H-14, the directions. You are given the graph of a position function, x of t, for a particle traveling along the x-axis. The output of the function tells you how many feet to the left or right the particle is from 0 at any time, where t is in seconds. Okay, so let's take a look at this. So this is the position function. The input is time, the output is where the particle is on the x-axis. So part A. What is the position of the particle at time t equals 6? So I just have to find an input of 6. I've got it right here. And then the output is 8. So I'll just say 8. All right, so positive 8. So it's 8 feet to the right of 0. What is the position of the particle at time t equals 13? So I got to find an input of 13, so right here, so -2. So it's at -2 on the x-axis, so 2 feet to the left of 0. Now part C. At what time or times is the particle at rest? Explain. Now, we are going to be needing to use both of these tables. So this one from the very last intro video and Susan's table. Okay, so at rest would indicate that velocity is 0. So at rest would indicate that velocity is 0. And velocity, guys, is the first derivative. So velocity is the slope of the tangent line. So and this is x, okay, that's the position function. So its first derivative, the slope of the tangent line here, that's what's telling us the velocity. Where is it 0? Well, it's going to be 0 here, and then it's also going to be 0 down there. Okay, so at what times is the particle at rest? Explain. At t equals 6 and t equals 13. Now why? Guys, when you're doing an explanation, you need to use a combination of the information on this table and the graph that is in front of you. If you're gonna use a certain graph to explain why a certain thing is true, you need to refer back to that graph. You got to pull from some outside information sometimes, which we're going to need to do with this table, and then you're also going to have to relate that outside information to the graph that you're given. All right, so our explanation needs to include because something about this graph that we're looking at. Okay, now the outside information. At what time is the particle at rest? Guys, we know that the particle is going to be at rest when the velocity is 0. So I'll be like, at these points, because the velocity is 0, we could even say v of t. How do I want to say this? Let me look at how I said it last year. I said v of t. Okay. At those times, because v of t is 0, but we need, remember, to tie it into this graph. Why is v of t 0 at those points? Well, because of what I just showed. Because v of t is 0 since x of t has horizontal tangents. Okay. So at t equals 6 and t equals 13, because v of t equals 0, since x of t has horizontal tangents. All right. I'll say at those points would maybe sound better. Make it sound better if you want to, because I'm not really, I don't know, it doesn't sound great. Now D, at what time or times does the particle, I should say seconds. I didn't on my answer key, but okay. Now part D, at what times does the particle change direction? Explain. A change in direction on the position, the change of direction is going to be on a sign change on velocity. Okay, a sign change on velocity. Okay, but guys, what about a sign change on velocity? That's where you're going to have to layer these tables here. Okay, so a sign change on velocity is going to be indicated how? Well, if you're just looking at this table, you're going to say, oh, it indicates when the particle changes direction, but I don't know, that's kind of unclear just from looking at this graph. So this is where you're going to have to refer to Susan's table. All right, so a sign change on, if you're looking at something graphically, a sign change on the first derivative is going to correspond with an extrema on the original. And that's what we're looking at right here. All right, so our explanation is going to need to involve, we're going to have to state yes because we've got a sign change on velocity. But why do we have a sign change on velocity? Because we've got an extrema on the original function. Okay, so for part D, at what time or times does the particle change direction? At 11 and 15 seconds. At t equals 11 seconds and t equals 15 seconds. Now, why? All right. And we'll say that, no, I'm wrong. Oh my God. Guys, I'm so tired. Sorry, this is the first day back. All right, I'm looking for the extrema on this. At t equals 6 and t equals 13. Okay. Okay, now, okay, we'll say because velocity changes sign, because velocity changes sign since x of t has extrema. Okay, I'm pulling in the information from this physics table, but then I'm finishing it off by referring to this graph that I'm given. What about this graph that I'm given is allowing me to make the determination ultimately? Okay, D. Now E. Over which intervals is the particle traveling right? A, B, C, D, E. Okay, well, the particle is going to be traveling right if the velocity is positive. How are we going to know if the velocity is positive? We're going to know if the velocity is positive, velocity is the first derivative, if the original function is increasing. Okay, so that's how we're going to know. A, B, C, D, E. So over which interval is the particle traveling right? Okay, so I am looking for where velocity is positive, which is going to be where this graph is increasing. All right, so it's going to be from 0 to 6, union 13 to infinity. All right, and the reason is going to be, okay, the first thing you're going to say is from this table, and then you're going to follow it up with using this table in order to relate it to the original graph that we're given. Okay, so this, because velocity is positive, we'll say because v of t is greater than 0, since x of t is increasing. Okay, now F. Over which intervals is the acceleration of the particle positive? Explain. All right, now I look here, guys. And I only see, so here's this physics table. I see a positive acceleration twice, but that is only having to do with whether the particle is speeding up or slowing down. There may be some convoluted way of using this information to figure out the problem, but it's better if you just use Susan's table, keeping in mind that acceleration is the second derivative, okay? So over which interval is the acceleration of the particle positive? They're asking you, when is the second derivative positive? And then explain, okay? So the second derivative is positive when the original function, which is what we're looking at, is concave up, okay? So it's going to be, so over which intervals, okay, so where is this concave up? Okay, so that's all downward parabola. Looks like that's an inflection point, so we got concave up there. So from 10 to infinity, 10 to infinity, because x of t is concave up. Because x of t is concave up. All right, now for g, over which intervals or interval is the particle traveling right with a positive acceleration? So here we're overlapping E and F. All right, this is where, okay, so I could even do like a little graph here, although you don't need to. So we got 0, 6, 10, 13. Okay, so we know the the particle's moving right here. Okay, the particle's moving right there. And then we've got positive acceleration from 10 to infinity. Okay, so our overlap is happening from 13 on. All right, so the answer for G is from 13 to infinity. Now we have to say why, okay? Oh, no, thank goodness we don't. Okay, so we don't have to say why. Alrighty, I will talk to you later, guys. Bye-bye.